Okay, so for first thing, we want to talk about the test that's upcoming on Thursday. I did release the Blackboard site. Hopefully you guys can see it now. And if you can't, let me know. But it is scheduled in room 152 on Thursday. And it'll be over all of the material that we've covered to date. Anything that we go into today, new, will not be on there, obviously. And depending on what section you're in, you're either in the 9 o'clock until 11:50 section, or you're in the 12 to 2:50 section. We covered a lot last Thursday, and I'll be glad to go over anything that you guys have as far as that before we move on to anything. But just make sure that you're paying attention to what you need to do. So if you haven't had a chance to read the lecture notes, you might want to review those before you get to the test. Hopefully you've read them. Then there's the assigned readings out of the textbook, and you can bring your book, and you can bring anything that we've done problem-wise or whatever. So all that's open note, open book. So I do suggest you get that all organized and have that. And make sure that you have a good working calculator. So I have people that have issues sometimes with either calculators or batteries. Make sure you check all that before you come, because you're going to be pretty busy on this test. So just make sure you have that. I will have my calculator with me, but that doesn't necessarily do anybody any good if they're not used to it. Okay, so make sure you got one that you're used to. All right, let's see if there's any questions about the test that I can answer before we move on, and particularly any problems. I'm glad to go over anything. So anybody question-wise, anything?
No, I'm good.
You guys all had a chance to look over, make sure that you know how to do units, make sure you know how to do bearings, azimuth type calculations. We spent time doing a traverse. You can count on traverse type calculations, side shots, inversing, direct routine, those kind of things. Does that spur anything anybody would like to see based on that? No questions. Okay. If there's no questions, because I'm going to have plenty of questions for you guys on Thursday, so just make sure. If you do have, if you think it's something while we're in session today, you can ask it. And also, I'll be around. Well, I can probably be available sometime through the day tomorrow to answer questions. So you can send me an email if that's an issue, or I can do maybe a Zoom conference with somebody later in the evening today or tomorrow. So, okay, well, if there's no questions, a couple things I want to go on, and then we're going to move on to some new material that's, again, not going to be part of the test material, but it's going to be building into the stuff that we're going to be getting into. So first thing is, if you've missed quizzes, you got an email from me Sunday that gave you the quiz location, the password that you need to access it, and you need to take that quiz. If you have taken quizzes 1, 2, and 3, and you see that showing up on your Blackboard site, just ignore it, okay? If you don't have a grade out there, then you need to make sure you pay attention to that. Those quizzes will be open until midnight Wednesday, and after that, they're zeros. I'm not going to go back and do it anymore, okay? So you guys need to take advantage of that. Only one person has so far, and there's quite a few of you out there that need to handle that. You will need to take, you need to do the quiz. It's a timed quiz. You have to enter the information on Blackboard and also send me calculations. Okay, so if anybody has any questions about that, you can talk to me later or whatever, but make sure you do those quizzes, because after Wednesday, they're not going to be open for you anymore. Okay, everybody understand that needs to do those?
I just wanted to confirm that you received my email and my quiz was completed.
Well, you already got a grade, so obviously you didn't look.
Oh, okay, cool.
Yeah, no, I did get it, Jacob. So, yeah, so that was great. So yeah, I did good. If you don't find the grade in there, let me know. But it should be in there. Okay. So yeah, everything was good. Okay. So anybody else, make sure you heed the warning because if you don't, you don't want to get zeros on quizzes. And also, those should help you a little bit prep for things. Okay. All right. So since last week we were not able to do the Traverse, we are scheduled to do that on Thursday a week from this Thursday rather. So we will be going out. Hopefully weather is going to be conducive and we're going to go out there and come whatever it takes. So we will be meeting in room 101 in the ATLC. And I'll of course be going over that on next Tuesday as well. So be prepared for that. Make sure you're dressed and all of that. We're probably going to have snow and it's probably going to be cold too. So just make sure you get that ready to go. I would look over that lab one. We're going to go ahead and do that control traverse. That's a very good lab to do. Now, what we might do is not do lab 2 because it's really kind of an introductory stuff or just kind of a review on stuff that you guys have done in the intro level stuff. So we'll probably skip lab 2 and do lab 3. So that'll put us right back on schedule with what we need to be getting into. So we really just scuttling that one lab won't be a big deal, but we will be doing lab 1 next week. And then we'll continue on with that. Okay, does anybody have any questions on anything before we go into some new material?
There was last Thursday we did a problem in class. It looks like a pentagon, and we did the building inside of it.
Yep.
There's problems on the test.
Well, that was a radial stakeout problem.
Yeah.
Yeah, so I'm probably not going to do any radial stakeout with you on this test, but you can probably have something like that in the second test because we're going to be starting to utilize that. So that's a really good question. But here's the thing about that. Number one is it's basically just inversing. Okay. So inversing is a huge part of what you'll be doing. Okay. So if you know how to inverse, you would know how to do that problem. But specifically, no, I won't have a problem like that. So that's a good call on that. Do you want to see anything about it though? I'd be glad to go over anything.
I mean, yeah, if we have time, that would be nice.
We have time because I was just gonna really, I just wanted to review today essentially, but then I thought, well, I don't want to waste that, so I'm gonna go into some stuff, that we need to get into for next week. So it's just getting ahead of the game a little bit. But
I just wanted to make sure that on the northings and eastings on those coordinate points, I took a little time to make sure that I was either adding or subtracting them right. I just wanted to make sure that I did that right.
what do you want me to just go through something real quick?
Yeah, that'd be good.
Okay. All right. Then now, can we just, do you have something specifically you want me to go? Let me just flip pages here. Do you have something specifically that you want me to go over or just make something up?
You can just make something up.
Okay. So you're saying, are you looking at an inverse problem? So in other words, I'm giving you 2 coordinates and you want a bearing and distance kind of thing?
We were talking about the homework problems.
Oh, okay.
16, 18, and 21.
Okay. Well, let me open up the book. And in fact, if I can, you're talking chapter 15?
Yes.
Okay. So let me just grab that real quick. Okay, you're talking about that one specifically. Okay. So, all right, let me, all right, if you have your book, I'm just going to do a picture out of that book real quick, okay? And then, and I'm just going to do something a little different than we had for homework just so you have it. So they've got a point E and D, and they give you coordinates, and then they have a building that's sitting up here. I'll label this here in a minute. So just to make this simple, he gives us coordinates On the corner of the building here, it's 0.12. That's 830 in the northing and 2770 in the easting. And down here, so this is 0.12. What we're doing here, this is E and D, this is E, and this is D. So we have 700 northing by 2500 easting, and the D part is 803,000. And those are all in terms of northing, easting, northing, easting. So again, this is specifically, I'm just doing it different than what he's actually showing, but it's the same process, okay? So let's assume we're gonna set up our instrument at E, backsite D, and foresight 12. So specifically, like I said, this is not a problem that we're going to have on the test, but this is going through inversing, so it's all good. It's all good. So what that says, we're going to sit here, we're going to backside here, and then we're going to turn an angle to E to 12. That's what we need. So we need to inverse that direction. And we also need to know what the information is from E to 12. So we need to get that line also, so we're going to need to inverse that. So what we would do is first get our backside. So I would need the latitude from E to D. So that would be the northing of D minus the northing of E. So remember, if you're just flipping those, okay? So in that case, let's see what we come up with. You guys can calculate it with me. I'm not going to write all that down, but D is 800 and E is 700. So that gives us a positive 100. So what does that indicate to us?
That means that we're going up 100.
We're going, right, we're going north, right? We're going due north.
Yeah, going north.
So east, departure E to D is going to be easting of D minus easting of E. And if we notice, that's going to also be a positive number, 3,000 minus what, 2,500. So this gives us a positive 500. So what does that tell us about our departure? That we're looking east, right? So our bearing is northeast. So the bearing in this case would be the arc tangent of the departure, which is 500 over the latitude. Calculating as we go. If anybody isn't getting a number, I am, let me know. I'm coming up with like 78 degrees, 41 minutes, and 24 seconds. And since this is positive, this would actually be a north bearing, and this would be an east northeast. Also remember, when you do this equation right here, you're never going to get an azimuth out of this. Okay, it's always going to be a bearing, and you have to assign the quadrant based on that, because this number is always going to be between 0 and 90 when you do that arctan. So just really pay attention to that, everybody, okay? Because that's important. So that's my backside. And
if we get decimals, you just want us to round up or down?
Always round it to the nearest second. We're never going to work to any higher degree than the nearest second, okay? So yeah, I had 24.24 seconds, but you know, I'm just going to round it. If it's 5, I'm going to round it up. If it's 0.5, if it's less than 0.5, I round it down, okay? Good question. Yeah, I mean, you aren't, that type of precision in an instrument you don't have, okay? You're lucky if you have a 5-second instrument, even though they're reading to 1 second, a lot of times they're really only calibrated to 5. So we always would work pretty much in a 1 second realm, okay? So that's good idea, good deal with that. All right, so what I'm gonna do down here is write this as a directional line. I'm gonna call that 78 degrees, 41, 24, and I'm going to convert it to an azimuth. So that's the azimuth in that direction, okay? Is everybody okay with that?
Yeah.
So what we need to do now is inverse the direction from E to 12. We need both actually, the direction and the distance if we're doing a pure or a true layout problem, okay? Which is what this really is doing in 15. Now, we're not going to see that until 2 weeks when we do our first building layout. We're going to use this concept. Okay, so this is just setting the stage, but it's all related to what we've been getting into. So we're going to do another inverse, and I'm going to need a latitude from E to 12, which would be the northing of 12 minus the northing of E. Okay, and again, as you look at that picture, it should be positive in both directions. So that's 830 minus 700. So I get a positive, you guys verify this with me, I get a positive 130. My departure, easting, E to 12, is the easting of 12 minus the easting of point E. Okay, so that would be a plus 270. Let me just mention something too here. It's not a big deal, but most people in the real world don't use A, B, C's, and D's for their control points, because you're going to run out of control points real quick. You only have 26 letters. So most people use numbers, just so you know. You would see that. All right, so the inverse tangent direction on this would be an arc tangent of the departure to 70 over the latitude. Now, as you look at this, if you think about this, if north is up, which we're assuming, this bearing has to be less than that bearing because it's going to be closer to north. So if you don't have that right, think about that, because if you flip those numbers, it could be different. Okay, so I'm getting, let's see what I'm getting here, 270. All right, I'm getting 64 degrees, 17, and it's also 24 seconds. Anybody agreeing with that?
Yes.
Okay. Now notice what I just said. This number has to be less than this, because again, if we look at north, the angle here is going to be less than the angle to there. So that does make sense. And in terms of an azimuth, this is also the same number, 64 degrees, 17 minutes, and 24 seconds azimuth. So we need the distance. We need the distance from E to 12. And using our latitudes and departures, we can simply get that. Okay, so we're using the distance equation, also known as the Pythagorean theorem, and that will take care of that. So you guys verify this, but I get like 299.67. Now again, you've got numbers that are going to float out, but essentially you're laying it out to 2 decimal places, you know, to the nearest hundredth of a foot anyway. So that would be what you would be using. Now metric people actually work in 3 decimal places. So if you are doing it metrically, it would be tens, hundredths, and thousands, or 10,000. So Okay, any questions on that? So that's the distance we would go as a layout from E to 12. Now what we also need to know is either this angle going this way or the angle that's coming around. And most people would not use this angle here, okay? That would be the angle to the left. So most people that I know, we always use the angle to the right. So who can tell me how are we going to get the angle that's going to swing around like this and come around like that? How would we get
Find
that?
that internal angle and then subtract 360.
Sure, that's a real easy way to do it. So to get that internal angle, as you called it, I would take the 78, 41, 24, and subtract from that my 64, 17, 24. My remainder is 14 degrees, 24 minutes, minus 360. And I'm coming up with 345, 36, 00. So what this says now is that instrument at E, backside D, foresight 12, you would turn this angle and you would go this distance and you could set a stake right there, and that should be theoretically the corner of that building. Okay. So this process is what we call radial stakeout. It's very powerful. We're going to employ it a lot as we get involved. We will not be doing it next week because we'll be setting actually a control traverse up. In other words, we'll be establishing these coordinates to be able to do this kind of stuff. But when you guys get out in the field the following weeks, I have a control traverse already established out there with good coordinates, and we're going to be seeing this same process. So that right there was a problem. Like I said, it's not going to be on the test specifically, but you know, inversing this kind of stuff certainly will be. That kind of stuff, and that right there. Does that generate any other questions anybody would like to see? That was a good question. It was a good example. We're all good on this, huh? No traverse issues, compass rule. Everybody know how to do the compass rule? Everybody know what precision is?
I'd be okay if we could go through it again, just to make sure.
What do you want to go through, Josh? I don't want to necessarily do a whole traverse. I did that on Thursday, but
Yeah.
Do you have something specifically?
No, since I missed Thursday, and I know that you guys went through that, but it's fine. We don't have to. I
Well,
understand.
no, I can do. I just don't want to go through a whole traverse. But is there a particular piece of it that you want to see?
No, I was just general.
Okay. Well, one thing, remember the steps that are involved in any traverse calculation. Okay. Let me fire this up real quick. Let's look at some PowerPoint stuff real quick. Maybe that'll answer a question for you. Okay. Because I'm not trying to not answer that, but like I said, we went through that on Thursday. So let's see. Give me a sec here. Gotta find it. I think it's in here. Okay, so the biggest thing with traverses, maybe it's not in this section. Might have the wrong PowerPoint. Yeah, let me grab another one. Okay, so this one, the biggest thing with traverse closures, just remember the steps, okay? Because the steps really kind of fold you through, and you can use these as handouts, okay? You might want to print this stuff out to have it, particularly this piece right here, okay? So this is, let's go ahead and do that slide from current. So this is showing you the typical steps that you go through in a traverse calculation. So now I might not give you a traverse where you have to do step 1, 2, 3, 4, 5, 6. I might bring you in right here and say, you know, okay, I've already done all of this up here. Calculate latitudes and departures and go on. Okay. So do keep that in mind. You want to have these steps available to you and know what each step is and what it's referring to, but it may not start from start to finish. Okay. So in a traditional traverse, and like the control that we're going to be laying out next week, we would do all of this. We'll balance the angles first, calculate directions, and it can do it either in azimuth or bearing, calculate latitude departure, determine linear misclosure and relative precision, adjust traverse and adjust coordinates or calculate coordinates. So if we go through that real quick, you know, remember we've got the angle balancing, and you know, some of you guys didn't do very well on that one quiz on this, so you know, make sure that you know what you're doing. First thing, make sure you know how to add angles, because that was probably half the battle. Some of you didn't get your angles summed up correctly. Also, remember, who can tell me what the theoretical summation equation is? I don't have that down here, but what is that?
It's a n minus 2 times 180.
Correct. So that's going to tell you the theoretical sum of any closed figure. Those angles should always equal that. So again, if you're blowing the actual sum, I mean, it doesn't matter what you're doing here, you're going to get the wrong misclosure. So make sure you're going to have plenty of time on this test. What I would do is probably calculate it once, write it down, and then recalculate it just to check it, because you don't want to, you know, have something like that going on. And I'm going to tell you truthfully, if I do something like a summation of angles, you're not going to come up with some really squirrely number. You know, you're not going to get 13 as a misclosure because it's not going to balance equally. I'm going to give you something that's going to be an even number that will balance out. So you get like a 2-second correction or a 3-second correction or something. So if you get something weird like that, that's probably on your part. Okay, just so you know.
Yeah, I think on that last test we did,
yep,
I added my corrections instead of subtracting them.
Yep.
Yeah, so I just wasn't paying attention when I finished it.
Well, what you didn't do is after you applied the correction, you didn't sum your angles back up. That would have shown you right away. Okay.
Yeah.
So, I mean, also remember, we've talked about a lot of these different checks and balances that you have throughout this whole process. Make sure you do them, because you know your answer before you leave the test if you do that. I mean, if you don't do that, if you just assume you did your correction properly, you got a 50-50 chance of going the wrong way with it. And so it's real simple to just check it and you're good to go. Okay. So that's a really good point, valid point. So I did see that. I saw two things going on in that test or quiz. You know, you blew your summation, or you applied the correction wrong, one of the two. Those were two issues. So watch it. You know, that's really important. And we're going to do an equal distribution. So that's what I said. If you're going to get a misclosure from me on this test, it's going to be something that's going to give you a nice equal number, 2 or 3, 4, whatever. Okay. So that's your first step. Second step, of course, is to calculate traverse directions using azimuths or bearings. So you would be given some initial direction, and then you would have to go with that. So again, I may have a problem out there that you're just doing something like that very simply. It's probably not going to be a traverse start to finish, and I'll tell you why. Because if you blow one aspect in the beginning, the whole problem's wrong. First time I taught this class, way back when, I did that in a traverse from start to finish, and half the guys couldn't calculate bearings. So, you know, at that point, the whole problem was wrong. So just, you know, be focused on that. I'm going to bring you in at different points within the traverse process. I hopefully at this point, everybody knows how to do bearing and azimuth calculations. Does anybody need to see anything relevant to that? Because I would certainly go over that if there's any issues. We're okay?
Yeah, I'm good.
And if you choose and you want to use azimuths, you can, unless it's specifically stated, hey, you have to use a bearing. Because remember, the azimuths very, very often are going to make your work a little bit simpler to deal with. But again, that's up to you, unless I specifically say I need this or this in that format, okay? So the next step is to do latitudes and departures. So this is the process where you have a known distance and you have a known direction. So in this case, where we're using these equations, remember, latitude is always a cosine relationship. Departure is always a sine. If you flip these guys, you're going to have problems. I haven't seen too much of that going on by anybody right now, but hopefully I won't see it on the test, okay? But remember, this angle, theta, can either be expressed as the bearing angle or the azimuth angle. You're going to get the right latitude and departure using either one, but the difference is, I think we all know at this point, when you're using a bearing angle, that bearing angle is only going to give you a positive result for your latitude and departure. So at that point, you're going to have to apply the sign based on the quadrant that bearing exists in. The advantage to the azimuth, of course, is that your calculator will calculate it properly, and you will get a proper positive or negative sign based on what the azimuth angle is. So again, just think about that. If you're using bearings, this is that little chart. Remember, northeast is positive, positive. Southeast would be a negative latitude, positive departure. So again, we're just saying that south and north is positive, negative respectively. And then the same thing with departure is east and west. You have west is negative and east is positive. All right, so once you do that, this is the next step, calculating linear misclosure relative precision. So we sum our latitudes, we sum our departures, we do that algebraically, and that's going to give you your air and latitudes, air and departures. And remember, when you do this, if you come up with a really large number, that's also going to be a mistake. Now, I'm going to probably give you something that you can see, that you can adjust, but it's not going to be 5 feet. So if you get something like 5 feet or even 1 foot, you're probably going to be wrong. You need to recheck stuff, okay? But I'm going to give you something. It's not going to be like 0.01 because that's not going to be enough to distribute if I gave you something, okay? And also make sure that you follow the sign, because the signs are critical when it comes to doing the adjustment itself. So when you sum them up, make sure you're doing it algebraically, okay? Linear misclosure, your air enclosure, either way, we express it as the air and latitude squared plus the air and departure squared square root. So again, you're just using that Pythagorean theorem relationship. The bearing direction of the air is less critical, okay? But what we've talked about quite a bit, and what you'll find is pretty true, is if the traverse tends to be longer in a north-south direction, you're probably going to have a bearing that's going to be between 0 and 45 degrees, okay? Because it's going to be closer to north. If your air, or if your traverse tends to be longer in an east-west direction, you're going to have a bearing angle that's going to be between 45 and 90. So you're getting, it's showing you which direction it is, and it should make sense because you're traveling longer in one direction than the other. So the air tends to follow with that. And again, it doesn't always work that way, but majority of the time it does, all right? So with this, once we have E, which is the critical component here, then we go and do what's called the relative precision. So remember, that's really defined as your air divided by your perimeter, your air enclosure divided by your perimeter, which if you do that, you get that small number. So you just flip it, 1 over x, or you can just divide perimeter by E. But what that relates to you is the amount of precision as number 1 in something. So we express this, we would say this is a 1 in 16,385. A lot of people would just round that to 16,000, or might call it 16,400. But remember, what this is specifically saying is that for every 16,400 units we travel, we can expect 1 unit plus or minus of air associated with that. And so hopefully everybody realizes that this is not a good precision right here. In fact, it would fail probably in all counts. I do think state of Ohio in urban surveys is 1 in 20,000. I think rural surveys, farmland, they actually let 1 in 10,000, just because it's you got more open ground and everything. So this might be acceptable back in the day, but I wouldn't call this an acceptable precision for any purpose. Okay, so the next thing was the adjustment. So we talked about 4 rules. We've only considered 1. So you don't need to know anything about the other ones. In fact, I didn't talk about anything other than the transit rule. And what I did relate to you is that the transit rule assumes that you're measuring your angles with a better accuracy than you are your distances. So when you adjust a traverse with a transit rule adjustment, it puts more correction into the distance component, and it keeps the angle pretty much the same. So the compass rule, what does the compass rule assume? Anybody know? So we said the transit rule assumes that the angles are better than the distances. What's the compass rule doing? Nobody knows? It pretty much assumes that the distances and the angles were pretty much measured with an equal type of accuracy. So in other words, the distance and there's nothing better. They're basically the same. That's pretty standard measurement by today's instrumentation. So when you're using a total station that's a 1-second instrument and an EDM that's built inside of that, you're getting good distances and you're getting good angles, and they're pretty equal. So what the compass rule will do is it actually adjusts both components. So it tweaks the distance a little bit and it tweaks the angle a little bit, and they're pretty much equal. Both things will change though. What you'll find is both will have a little bit of an adjustment placed in them. So the compass rule adjustment, it's a 2-step process. So to calculate compass rule, first we need to calculate corrections. Okay, so the corrections are your air and latitudes for latitude correction, or air and latitudes divided by perimeter times the distance of the line you want to correct. And so remember, you don't have one correction for the whole traverse in latitudes. There's a unique correction for each distance. What is true about about the correction with respect to the distance? Can anybody tell me what's true about the correction? Nobody can tell me? Well, the air and latitudes divided by the perimeter is a constant. The only thing that's changing here is the distance. So as the distance gets greater, the correction gets greater. Okay, so it's a direct proportion. As distance increases, you expect more correction in latitude. Same thing with departure, because the air and departures divided by the perimeter is a constant for the departure condition. As the distance increases, the correction for the departure increases. Okay, so you have that. Also, the negative out here is just flipping the sign. So if your air and latitudes are negative, all of your corrections should be positive. Okay, so we've gone over this quite a bit, so hopefully everybody knows how to do this. When you adjust each latitude, you take the latitude of the course you want to adjust, and you add to that the correction for that line. Okay, so if I'm adjusting latitude 1 to 2, I'm using correction 1 to 2. For latitude 2 to 3, latitude 2 to 3. And the same thing works for the departure. What should be true about your adjusted latitudes and departures when you get done?
They should,
Go ahead.
isn't it, they should add up to the some of the internal angles?
No, not at all. Anybody help him out? If I sum my latitudes and departures after I've adjusted them, what's going to happen?
Oh,
Oh,
they'll cancel out and be 0.
They're going to go to 0, right? And if they don't go to 0, then either you blew a correction or you didn't apply it correctly, okay? So make sure you check that. So that's again, easy place to make a check, easy place to adjust it, right? Now what's happened when you've adjusted it, each angle, each interior angle or azimuth, however you want to look at it, and each distance has been changed just a little bit. And of course that depends on your precision. If you've got a really, really low precision, it's going to adjust them quite a bit. Okay, so it's not just a little bit once you get into it, okay? So the next step or the last step would be calculating coordinates. And basically we're just using this equation that says, you know, your point B is going to be equal to the point you're coming from plus the latitude that corrects them or connects them. And again, you're using algebraic signs here. So if you have a negative coordinate and a negative latitude, you're adding them together. You get a negative coordinate here, but we always are using positive coordinates, so we shouldn't have any negative coordinates. So we really just have to consider the sign of the latitude and the sign of the departure as we add them, okay? So that's kind of the situation that we went through on all of these. And then if you're using X's and Y's, that's what you would use. Notice you're flipping your departure and your latitudes. We're not going to be using X's and Y's. Everything's going to be northing and easting. That's what layout people use by and large. And that's what you guys are, that's all we've been talking about. So don't worry about X's and Y's. All right, that's kind of a review. Josh, is there still something you would like to see based on any of that? Well, maybe not. Okay. All right. Does anybody want to see anything else? This little section on sheet 2 is pretty important. So make sure you have this one available. Let's go to let's see. Let's go to the sheet. Oop, that's the wrong one. Okay, close that one. Let's see. Okay, so from the coordinate geometry stuff that we got into, let me just give you a couple of key equations here. We did talk about some of that stuff. By the way, any coordinates that you see are going to be rectangular coordinates or polar coordinates. You're not going to be dealing with stations type stuff. When we get into highway stuff, linear alignment, we're going to see this, but we don't have to worry about this. So you can kind of, this is just was informational for now. It's not going to be as important. All right, this is important stuff. Let's just make sure we go through this. So you will be looking at the different types of COGO calculations, which we just did an example from, but primarily the inverse routine, which allows us to get distance direction, and the direct routine, which allows you to take a known distance in a known direction, and then with a known starting point and get an ending starting point or a coordinate value. And I just went through an angle concept. I didn't go through any kind of intersection stuff with you. These are powerful types of things, but we don't have time to mess with those. So we're not going to get into that. And I did kind of show you an area problem the other day, but again, I'm not going to worry about that right now in this test. So in this piece right here, inversing direction is important. Now I gave it to you in terms of analytic geometry, but we really are going to be utilizing the surveying kind of concept. So this is your inversing direction. And again, hopefully everybody has memorized this by now. It's your departure over your latitude, and this is always a bearing angle. And of course, latitude is going 1 to 2 is going to be 2 minus 1. Another term of another way of expressing that is delta northing, delta easting. But you need to make sure what you're saying with that, 1 to 2 or 2 to 1. So that's your inverse direction. Inversing distance. Well, of course, that comes into play also. Memorize that little chart if you don't already know that. That's important for inversing. Distance is very simple, okay? Distance is just your latitude squared plus your departure squared square root. The beauty of distance is whether you flip your latitudes and your departures right or wrong, you're always going to get the right answer, because when you square a negative number, it's always going to become positive anyway. So if you inversed in the wrong direction, the distance is still going to be right, but for the direction itself, that's going to kill you. So you got to be careful with that, okay? I think out of this sheet, there's other things here. There's other issues here. Okay, here's the direct routine. So when you're doing a direct routine, you can get a latitude from any point to any other point by taking the distance times the cosine of the direction. Okay, so we've already seen this. Again, hopefully this is starting to really be cemented in everybody. Okay, so just have this available too. The things we didn't do on this, area calculation, I kind of talked about that the other day, but don't worry about that for this test. That's not going to be important for it. Okay. All right, so didn't talk about state plane. I just, maybe I'll talk about that a little bit next week, but I don't really want to get into that right now, because that's going to just muddy the waters really for what we need to get into. All right, so that's kind of it for the test. So any questions at anything anybody can think of right now?
I'm good.
Okay. All right, so I do want to introduce a couple of things we can start thinking about now. This should be this would be stuff that we'll be starting to see in the next couple of weeks. So I'm not going to worry about again, don't worry about this stuff for the test. And I did open up week folder 6. So if you guys want to look along at this, there should be, you should find your 6th folder open. And in there you have these lecture handouts, which I'm just going to kind of go through these. So these are going to start to talk about leveling. First, we're going to talk about leveling, and I'm probably going to get not too very far into this. But we're going to start to use this again, and then distance measurement, and then ultimately angle measurement. Okay, so let me see how far I get with this. If not, I'll pick up with this on next week. So I just want to not waste the time today. So let me go to my PowerPoints. I'm going to open up my PowerPoint slides. Nope, wrong one. Okay, we'll do a little bit here, and then I'll stop the recording after a little bit, and we'll get started. So let's see. All right. So, this is technically what we're going to start to do as we do more layout. So it's kind of broken down into 3 major things that this section is talking about. We're going to talk about elevation measurement. We're going to talk about distance measurement, and we're going to talk about angle measurement. So you've done all of these things before, and I think the first week alluded to this, but I want to pick up a little bit more specifically with this. Okay, so leveling techniques is where you're determining, first of all, when you're talking about leveling, what you're talking about is determining a elevation above or below what we call a datum. And anybody tell me what a datum is? Anybody know what a datum is? Nobody ever heard that term? Nobody knows what a datum is? Wow. Okay. A datum is just a reference surface. So when we talk about elevations or leveling, what do you hear very often is your datum? I know you've heard this term before. In fact, I think we've mentioned it before. Typical datum surface for elevations. You talk about being above it or below it. If you're below it, you get water. Nobody knows what I'm talking about?
Oh, sea level.
Yeah. And usually they express it as mean sea level, not just sea level, because sea level varies wherever you are. Okay, so it's like higher in the West Coast than it is in the East Coast based on what you call your geoid, which undulates. So it's not just like a flat surface kind of thing. So when we do construction, a lot of times we're not referenced necessarily to mean sea level because, you know, here in Ohio, we don't really care what mean sea level is because we're 400, 500, 600 feet above it. So we might have a relative, datum, or we might have a project datum, okay? So no matter what your datum is, if you're determining levels or information rather, elevation from one point to another, there's basically two ways of doing it, okay? And you can use a third method. I'll just briefly talk about it, but differential leveling is probably the best methodology. It actually reads vertical distances. You can also use a steel tape, and you can just run a steel tape vertically up or down a column line, for instance. That's actually a very good method of getting an elevation from, let's say, ground level up several floors up. Differential is where you're using an instrument actually measuring, and that's broken down into what we call profile leveling and three-wire leveling. So there's different methods there, but they're basically all using this concept of differential. Then trigonometric is where it's what we call an indirect method, because you're not actually measuring elevation, you're measuring something else. And from that, you're getting a leveling or an elevation value. And then there's sources of error associated with leveling, so we'll buzz through these. Okay, so in distance measuring, we're going to talk about steel taping techniques, electronic distance measurement, and sources of error. And I don't know how far I'm going to get in this today, so we may just pick up with this on next Tuesday. And so for elevation measurement, and something, there should have been angles on there. Oh well. Okay, so elevation is another way of expressing what we call vertical distance. And vertical distance is the distance that would be measured along a vertical line. So if you remember, in the very first days when we talked about surveying, when I started, I gave you some basic definitions, and one was a vertical line, and that's the line that follows the direction of gravity at a point. So if you take a plumb bob and suspend it freely, the string itself is generating a vertical line for you. Well, that's going to be important on next Thursday, because we're going to be utilizing plumb bobs to get sights, backsight and foresight. But when you're talking about elevation, if you're saying vertical distance, you're basically measuring that distance along that plumb bob string, if you will. That's your vertical distance. So there's three primary types of leveling, as we said: steel taping, or sometimes referred to as chaining, that's the old term, differential leveling, and trigonometric leveling. Anybody know why they use the term chain for steel taping? Anybody know that answer?
Did they used to use chains?
They absolutely did. In the original days of surveying, we're talking late 1700s into the early 1800s, they did use a chain, and it was broken down into what were called links. So yeah, that was we using, and that was once the steel tape was developed, probably early in 1800s. It displaced that completely. Federal government still uses the chain as the unit of measurement, though, for all the stuff they do. I think I've mentioned that before too. So if you're steel taping, you're directly measuring a vertical distance. So you're reading it directly. It's really a good method. The thing about it, though, is that you have to make sure that the steel tape is being held vertically. So if you are out of the vertical line, in other words, if you're doing a diagonal distance, you're not getting a true vertical distance. So you got to be careful. But like I said, if you had 5 floors up, and you wanted to get an elevation up to the 5th floor on a building that was being constructed, you could theoretically just drop that steel tape along a steel column and measure it, very precisely, because that steel column should be plumb. In other words, parallel with the vertical line, and read it right on it. So that's a great method. Differential leveling is direct, and what you're doing is reading a direct vertical distance in this technique. So if we look at, let me show you a picture here. Again, just a real quick schematic. of what we're looking at when we talk about this. You use an instrument called a level. We typically use what's called an automatic level. So if you have, let's say your ground line here, you have your automatic level set up. That's just a crude automatic level. And I've got a tripod leg here and a tripod leg here. When you level this thing up, what you're getting is a horizontal line of sight. And you have a known point, and you put a rod, a level rod here, and you have an unknown point here. Place that rod over here. So what you're doing in this method, you're reading this distance, which is called your back sight first. So if I know this elevation here, I'm taking my back sight and adding it to my elevation. So your elevation plus your back sight, and that's again just a vertical distance right there. That equals this line of sight here, which we call my HI, which stands for height of instrument. So anywhere I turn that scope, basically I'm looking at the same elevation. And then if I get to this unknown point here, I'm going to read this rod intercept, which we refer to as our foresight. And so we're going to take the HI minus the foresight, and that's going to give me the elevation of that point down there. This is differential leveling in a nutshell, and it takes two equations. HI is equal to back sight plus elevation of known point. Elevation of unknown point is going to be equal to the HI minus the foresight. So you guys have all used this, and these instruments are so cool because when you level them up, they're real easy to level. You don't have to worry about being over a point. So it doesn't matter where we are here. What we do try to do though is keep the distance here and here balanced. Okay, so we would like that to be the same number, which you can see isn't true in my case. Why is that critical? Does anybody know why that could be an important thing? It has to do with errors associated with that instrument. So if you are closer in one direction than you are in the other, if this thing's slightly out of level, the amount of error here will be less than the error here. So if you keep them balanced, you'll have the same amount of error, and because one is a plus and one is a minus, they cancel. It's kind of like that concept I was talking to you guys the other day on Thursday about double centering, where we flop the scope when we turn angles, it gets out that scope eccentricity. Well, this keeping these guys balanced basically does the same thing. So it negates or gets rid of any error that you have associated with your level or your setup. That's a really good thing to kind of know how to do. A little bit harder to do than it seems while you're out there. Oops, see, didn't think. All right. So that's a direct, that's differential leveling. So differential leveling can occur either by doing what's called running a loop or running a line of levels. And then you can do a process called profile leveling and then three-wire leveling. So they're all differential techniques. They use the same concept though. They use exactly what I just showed you. You add backsight to elevation and you subtract the foresight. It works all the same way. The difference is that if we're running a loop versus running a line of levels, how that proceeds. We're going to be doing lots of loops while we're out there, but just to show you real quickly, if you are looking down, like say from an airplane, and you have a point here and a point here and a point here, what you would do is you'd set your level up between your points, take a back sight, take a foresight. So that basically gives this elevation, it transfers it to here essentially. Pick up your instrument, take another back sight, and another foresight. And then I'm going to pick my instrument up one more time, do the same thing. Back sight, foresight. And this is what we call a loop or a closed loop. So it's just like a traverse. The beauty of that is that by doing that, you're getting a check. Because if we start at elevation 800, as we come around, we have to end back at 800. And if we are higher than that or lower than that, we have what's called a loop misclosure. So we use the concept of misclosure in elevations and leveling just like we do in traverses. Okay, so that's called a loop. Now, if you contrast that with running a line of levels is a little different. What you're doing in this sense, you're saying, I have a benchmark here that's got a known elevation on it. So that's a good benchmark, and somewhere down the road, maybe 5-6 miles, I have another benchmark that's got good elevation on it. So what I do is I set up my level, back sight, foresight, set up another level, back sight, foresight, do it again, and do it again. So what we end up doing is we have a starting benchmark, we have an ending benchmark, we still have a loop essentially, as long as this benchmark and this benchmark are in the same system. If they're not in the same system, then you're an open loop, it's not closed. But if these are in the same system, this is a really good way of doing this. And like I said, if this was a 5-mile run, you don't want to go 5 miles back to loop it back. You could, but if you conveniently have two benchmarks, you can start at one, tie into the other. This is called running a line of levels. So this is a good method. The profile leveling, which we're going to also use quite a bit, I'm sure you guys remember that. What this allows you to do is if you've got, let's say, stakes along an alignment, let's say this is like a back a curb, and you need to get elevations on all of these guys. You set your level up, hit your benchmark, get your HI, and then you shoot, and you shoot, and you shoot, and you shoot. Notice I'm not picking up. I'm going to get to a point where I need to pick up, and I can continue. This keeps me from setting up my level at every point, especially if these are only 25 feet. Now the problem is that this shot, and this shot are considered side shots, so there's no check in the quality of these, only the ones that are part of the loop. So there would be a check here, and then you continue. But we do this profile concept because it's quick, and it's a lot less setups. Yes, you can make mistakes, and certainly I've made plenty of mistakes. So that's not necessarily foolproof. So that's how that would work, though. And we're going to be utilizing that process. We're going to use that process quite a bit. Three-wire leveling is a method of where I know you guys have all done leveling, so you know what I'm talking about. When you look through the level, you have crosshairs, and you usually read the middle crosshair. What three-wire leveling allows you to do is there's a little upper hair and a lower hair on that. You read all three of those. And by doing that, when you take the three of them, add them together, and divide by 3, it should equal the middle reading. So it keeps you from making mistakes. So this is just a technique that's really good for running control, and it keeps you from making any reading mistakes on your levels. I think you guys are going to find out once we start doing levels. Leveling seems to be, it's actually very easy, but it seems to be one of the harder things people do at first. Just saying. All right, so the typical differential leveling equipment that we'll be utilizing is a level, automatic level. That's what we're going to be utilizing. They also have what are called tilting levels, and the newer levels are digital levels, which are really cool because they have a rod that's basically like a barcode, and it just reads all the information, so you don't even have to read anything. But we'll be using little automatic levels, which are great. They work really well. You have a tripod, you have a level rod, couple different types of level rods. The ones we're using is called a Philadelphia rod. I don't know where it got that name, but that's the one we use, where it boots up to like 14 feet. A linker rod, they're kind of cool. They're used in construction. They have a face that actually moves, and they're a little bit hard to adjust. I have actually some at college. We probably won't be utilizing them. We'll be utilizing the Philadelphia rod primarily. We have a hand level and a rod level. So the rod level is a little level bubble that you place next to the rod, hold it with the rod, and it allows you to keep that rod vertical, in a vertical position. Without that, you could be leaning it in slope direction, and so what you're doing is getting a false reading by doing that. The hand level is important when you're setting up on an uphill situation, because if you are setting up uphill, it's real easy to get your level too low, and then you end up setting it up about 5 times before you get your location where you want to put your level, or you could be shooting over top of a rod, either way. So the hand level, you just throw a hand level out. If you're seeing too low below your point, it means you need to go up the hill a little bit more. So these are really nice little devices to use when you do leveling. Okay, so differential leveling, some beautiful things about it. It's a direct technique. It's used where high accuracy is desired, and it's a very quick method. Once you learn it, it's real easy. All you're doing is measuring back sights and foresight readings. That's it. And then setting up the level, as I said, you can place it anywhere. Leveling it up is real quick. Now you're going to find on next Thursday, if you haven't leveled up a theodolite in a while, it's going to be a pain to do, because you have to have 2 things happen when you're doing a theodolite. You have a very, very sensitive level vial that you're dealing with, and you have to get that thing over a point specifically. So if you're not over the point, or you're not level, or both of those things going on, when you're turning angles and getting distances, everything's not right. With a level, you don't have to be that good about it. You can set it up anywhere, and you can level it up quickly, because they're inside the instrument. There's actually a prism that is suspended by Teflon wires that actually is free to swing, and you don't have to be perfectly level, and it'll still give you a level reading. So it's a really beautiful process, the way it works. Okay, so the equations, we already talked about this. You determine your HI based on any elevation value that you're at. So you take your elevation plus your backside reading, and that gets you your HI, your height of instrument, and your elevation of any other point from that is going to be your HI minus your foresight reading. So 2 equations, very simple, easy to use. Although notes tend to be a little difficult for some people. So we'll take a look at that. So for closed loops, what's always true is that your misclosure is going to be equal to your final elevation minus your starting elevation. So again, you start at 800, you end at 800, then you got a 0 misclosure. But if you end at 802, or let's say 800.02, your starting elevation was 800, you have a 200s bust. Another way of looking at it is this. You've got 2 checks. If you take your back sights and sum those, and you take your foresights and sum those, and your foresights are always negative, when I add those 2 together, they should equal 0. So it's kind of like errors and latitudes and error and departure, if you will. So if I take my back sights and sum them, and I take my foresights and sum them, that's a negative sum. When I add those, I should get a misclosure. By doing this right here, and doing this where you take the final elevation minus the starting elevation, and you take your sum of your back sights and your foresights, those 2 numbers should agree, both in terms of magnitude and sign. So if you're getting like a foot here, and you're getting in your misclosure of your back sights and your foresights, and you're only getting 500ths, you made a math mistake. So the one equation will check the other in terms of making a math mistake. And when I was out in the field working a lot, the first thing I would do with level notes, I wouldn't calculate elevations. I didn't care about those. The first thing I would do when I got done running elevations was I would sum my back sights, sum my foresights, and check them. That's the quickest way to make sure that you don't have a bust in your levels, and then you can come back later and do your elevations. But it's beautiful because the one is a math check against the other. Okay, so you guys should be aware of this. Now this is the thing that we're going to be doing a lot of elevations once we get out there. Not on this first lab, but we're going to be doing it on every other lab. We're always going to have it. So this is a typical type of differential level notes that you've seen. You have a station column, or that's just an ID column of what you're shooting. There's your backside column, your HI column, your foresight column. And the rod column is only used if you have profile leveling. So if you're engaged in profile leveling, you'll use that rod column. If you're not, we just ignore it. Elevation, of course, is the elevation of the point. So what I'm looking at here is primarily just backside HI and foresight. Now, different people do this differently. I do it a very specific way, and I think your author he does it a little differently maybe, but in general, we're all doing it the same way. But it's just kind of like, it's almost like a checkbook. I'll show you what I mean by that. If you've got a checking account kind of thing. So here's an example. We started at benchmark A, and we took a reading at benchmark A of 6.77. So benchmark A has an elevation of 528. Now these notes right here are already complete. So as you're running these things, it's a lot different process because you're going to see it's going to be a little bit harder as you're writing the numbers down. But so what I'm doing here is, to get the HI, I'm essentially taking that 528 elevation, adding the 677 to it, and putting it right in the HI column. And typically what I'll do is, in the backside, to help me, I'll put a plus where it says backside, and I'll put a negative where it says rod shot, or foresight rather. That way that keeps me also where I need to be. Now the other thing I do, because you take the first shot that you take in the set of notes as your backside, there's no foresight. A lot of times I'll put a line right through the foresight column so that I don't deal with that. So I don't know if I can, let's see, does that allow me? Yeah. So in other words, what I'm saying is, I'll put a line right there, and I'll put a negative sign here, and I'll put a positive here, so that I know what's going on with that. And then what we're saying is, we're going to pick up, we're going to pick up the instrument. Well, actually, we haven't picked up the instrument. We're going to take a reading on the foresight. So this is the foresight reading. So that was the first backside reading. This is the first foresight reading. So what you do is take this elevation minus that, and you write it here, okay, in that point. You picked up the instrument, put it at what's called a new TP, that stands for turning point. So you re-level it, and you take a backside on the last point that you were sitting at, and then you take that elevation, that 530.54, plus the 745, and you get the new HI, new foresight, you just pick up. So ultimately, this is a closed loop, because we started here at A, we ended here at A. So notice, when you're doing these notes, what we're doing is we're taking and summing this column right here. So this gives me a positive 2463. If I didn't make a math mistake on this, I hope I didn't. And then I sum these up, and I get this number here. So when you add them algebraically, it tells me I'm getting a 0 misclosure. So also, if you do the other step, it says take the original elevation, bring it down here, subtract the one from the other. This should also give you 0. These two numbers should agree. If they don't, you've got a math mistake. So that's the beauty of how this process works, okay? So the types of differential leveling, or profile leveling rather, it's a type of differential leveling. Like I said, it's used to define elevations, usually along some kind of line, like back a curb, center lines, those kind of things. But you don't want to set up every time. If I've got a stake out there every 25 feet, I don't want to set up every time I'm between two of those. If I have, let's see, a mile of pavement, and I've got stakes every 25 feet in a mile, I'm going to be out there all day. So what I'm going to do is cheat, basically, by just setting up so I can shoot what we call rod shots Another name for this is what we call an intermediate foresight. So rod shots also have a negative connotation to them. And this is useful when we're doing what we call grade stakes. What that means is you're setting out stakes to be graded, like say for the back of curb elevation or center line or something like that, pipelines, any of that kind of stuff. So this is an example of those types of notes. So in this case, notice we set up somewhere between benchmark A and this turning point right here, okay? Right here, turning point. So when my instrument was set up here, I took a back sight and then I shot a rod and another rod and another rod and another rod. So what's happening is these are all negative. So remember, rods are going to be negative, foresights are going to be negative, these are positive. So you take your elevation plus your back sight and you get this. That gives me my HI. This HI is used for every one of these right here. But I'm not gonna calculate these first. I'm gonna ignore these first. So what I'm gonna do is subtract this from that, and it's gonna give me this guy right here. So then I'm gonna pick up, I'm gonna do it again. I'm gonna take this elevation plus that turning point, gets me the new HI. I took a bunch of rod shots and I did to a turning point. So again, I'm gonna take that guy minus that, and it's gonna give me this. Then I'm going to do another setup, and I'm going from A to B. And what's happening here if I'm going A to B? Am I doing a line of levels or am I doing a loop?
It's a line because you're not going back.
Correct. Right. Now, I want to show you what's going to happen here. These notes are going to be a little different. So I did one setup here. This is my second setup, and this is my third setup. So I went from the turning point in, so I'm taking this back, gives me my new HI. I'm going to subtract this, and there's that, okay? So notice if you take this guy and subtract it from your final elevation, you don't get this. This number, where's that number coming from? Anybody know? This is the published value of what would be benchmark. So in other words, I might go to the city of Cincinnati and they have a benchmark book, and in it says, okay, this elevation should be 360-301. So I take what I found my notes to be. I started at this elevation, which that was also a published number. And I take that number, run it through. When I compare this to the published, the difference here, there's my actual misclosure. Notice if I sum my back sights and I sum my foresights, they don't give me the same number. What this is showing me is the vertical difference between benchmark A and benchmark B. That's what it's showing me. So it's not showing me the misclosure. That only works for a closed loop. So notice it says, doesn't say misclosure here. It says vertical difference, okay? And I could take published value of this guy minus published value of that guy. It should theoretically be that number, but it'll be off by 0.03 of a foot. This is the more important number right here. That's the number that I'm using for my actual bench. So now notice what I need to do is come back here and I need to calculate elevations here, here, and here. So this is where people get confused a lot, but what you do is you're going to store this number in your calculator and you're going to subtract that from it, and it's going to go here. And you're going to subtract that from the same number, and it's going to go here. You're going to subtract that. Notice nothing's changing. You're using that HI as a constant, okay? And so if we go to the next picture, it shows you how that was done. Okay, so again, remember, this number is being used to calculate all of these, and it's not, you're not moving it each time. That minus that equals that. That minus that equals that. And when you get down to this next one, then you're using that HI for those points. Okay, and for this one, HI here, HI here. So if you're doing profile level notes, what I always recommend you do first is ignore these numbers right here and just go through the loop. Do your elevation, HI elevation, HI elevation, and your misclosure. always proof your misclosure before you do your rod shots, because otherwise you can get really messed up. All right, and we're gonna see this process as we get out there. We're gonna be doing this a lot. Okay. All right, so 3-wire leveling, as we said, it's just a method of differential leveling. Basically what you're doing is you're reading your upper, middle, and lower crosshairs. So it's very useful for precise work. If we look at, let me draw a little picture here, because I know you guys have seen this before, but we'll see this when we get out there. If you're looking through a traditional level, let's see. Oops. I'm looking through a traditional level. What I'll see is crosshairs. So you have a vertical crosshair, and right in the middle of your scope, you usually have a horizontal crosshair. It's usually bigger, and then above you'll have a little smaller crosshair here, and another smaller crosshair here. And this is the one you traditionally read. So when we're looking at a normal, this is the one you're reading. This is your middle crosshair. So when you're doing 3-wire leveling, you're going to read this guy, and this guy. So this is your upper crosshair. This is your lower crosshair. And this is your middle crosshair. So what's cool about 3-wire leveling is if you take your upper crosshair plus your middle crosshair reading plus your lower crosshair reading, you divide it by 3, it should approximately be your middle crosshair. And if it's not by a great amount, then you blew one of these readings. What people can do when you're reading, and I'm sure some of you have probably made this mistake, when you're out there just doing a single simple differential leveling, not using the 3-wire leveling process, instead of reading this, you read this one. And if you read that one, you've blown the whole level loop. And it's real easy to do if you're not paying attention. So 3-wire leveling keeps that from happening. That's the beauty of it. By the way, these guys, that crosshair, the upper crosshair, and the lower crosshair, these are referred to as stadia hairs. So if you've never heard that term or heard that before, these are called stadia. And stadia is a process where you can determine distance. So if you read your upper crosshair and your lower crosshair and you subtract them from each other, that difference multiplied by 100 will tell you how many feet you are from the instrument to the level rod within a plus or minus a foot or two. So it's not perfect, but we used to use this process called stadia for doing distances all the time. Nobody uses it anymore because now everything's EDM based. Okay, so again, here's that equation. Upper plus your middle plus your lower divided by 3 should agree with your actual middle reading. Okay, and again, just like I said, your upper reading minus your lower reading times your stadia constant, which is in the United States, it's usually 100. That tells you you're 100 feet. Okay, trig leveling. We're going to go ahead, we'll just do this, and in this I'll probably just go ahead and finish that for today. This is a technique that is giving you an indirect measurement of elevation. So instead of actually measuring elevation, you're measuring other things. And primarily what you're going to be measuring is a slope distance. You're going to be measuring a vertical angle, usually a zenith angle. You've got to measure an HI of the instrument, and you got to measure a rod height. So there's a lot of things you're measuring just to get an elevation. So it's not as good as differential leveling. But what's nice about it is it gives you quick results, especially for large elevations changes. So for the early days when they wanted to know the height of a mountain, they would do it trigonometrically, because to run differential levels up a mountain and down a mountain would take maybe weeks, maybe a month. So it's a lot quicker, a lot easier if you use trigonometric leveling. So there's some equations your vertical distance, you got to calculate that first. So you have to measure the slope distance, and you have to measure the zenith angle, and it'll calculate this. Now, when we're out with the total station, it's going to do that for you. So you actually will just get this spit out to you. It just spits that out. But what it's doing is, keep in mind, is it's doing a slope and a zenith. To then get an elevation, you're going to take your HI that you measure, your vertical difference, and your rod, and you're going to add them algebraically. Now notice this is plus, and this is minus, but this actually could be plus or minus depending on whether you're looking uphill or downhill. So if your vertical distance is uphill, if you're looking uphill, your vertical distance is plus. If you're looking downhill, your vertical distance is minus. If you're using a zenith angle, it's going to give you the proper sign. It'll give you, because it's like using an azimuth in that point. So let me show you how this works. And with trigonometric leveling, I'm just going to do a graphical sketch here. But you're going to use typically a total station, tripod, reflector, prism pole. If you want to get some more into some of the errors that are associated with EDMs, you would need a thermometer and a barometer. You would also need a folding rule, because that's going to be used to determine elevation change on your, or HI rather, in rod. So let's take a look at a diagram on this standpoint. And we'll probably use a little of this when we get out in the field. But we're going to, by and large, be using differential leveling, because it's a better method, especially if you're doing some kinds of, most of the types of construction. So here's kind of a schematic of what we're looking at. So let's say we're going uphill like this, and we've got an elevation point up here. We don't know its elevation. We do have an elevation down here. We'll call that A. So we have the good point of elevation there. So we're going to set up our instrument over top of that point. And what we have to do is measure this distance, which is referred to as my HI. So we're measuring the distance from the point we're sitting on to the center, optical center of the scope. And now on a total station, you usually see a little dot on the outside of the standards, and that's the point that you're measuring to. We take a rod up here, plumbing pole. Hopefully it's not bent like that, and a reflector, and you measure this distance from the ground to the center of the reflector. That's what we refer to as the rod. You're shooting the slope distance, and you're measuring a zenith angle. So this is my zenith. So we get the zenith angle. And what it allows us to do is, if we know this elevation, we can calculate this distance right here. This is my vertical distance. So we can see that if this is B up here, the elevation of B is going to be equal to the elevation of the point you're coming from, elevation of A, plus the HI. Okay, taking that plus that. Then in this case, I'm looking uphill, so I'm going to have a plus vertical difference. And then that would get me from here to here to here. And then in this case, notice the rod is going to be negative, and that would give me the elevation. Now, if you look at this, there's a lot of sources of error here. I could measure that not very well. I could measure that not very well. I've got a slope error that could happen. I've got a zenith error that could happen. I've got a vertical difference calculation. So with all of these kind of things, there's a lot of plus or minus going on in here. So we don't necessarily want to use this for really precise work. A lot of people out in the field use it though, because it's quick. And if you're grading, let's say sewer line stakes or something like that, if you're just off a couple of hundredths on your elevation, it's not going to matter. But if you're doing that through any type of precise control, this is not a method you would want to use for control. Okay, let's put it that way. For construction layout, yeah, it's pretty okay, depending on what you're doing. I don't know that I would want to do it for everything. Okay. Okay, so some sources of error, and then we'll stop here for the day. There are what we call refraction sources of error. So what happens is the curvature of the Earth creates an error because we're actually looking at we're kind of looking at a horizontal line of sight, but when we hold our rod out there, you're getting a curved surface. So there's an error based on distance. Refraction also, what happens is the light rays bend the horizontal line of sight down. So what's happening is it actually corrects to some point the effect of your curvature. So this can be pretty significant, and this kind of corrects it. So we have what's called a combined effect, right? In general, you don't have to worry about any of these because unless you're shooting distances over 1,000 feet, you're not even going to see this for the most part. And also, if you are keeping your back sights and your foresights balanced, these just cancel out, okay? So we don't worry about it because actually the levels that we're using, they're probably going to be less than you can't push them much more than about 300 feet. You won't even be able to read your rod beyond 300 feet. And if you calculate these things and using 300 feet, these errors are so significantly small. This M, I believe, is in kilometers, and that's in thousands of feet. So by the time you take those numbers and calculate them, they're really, really small. So we don't worry about this, but if you're doing really, really long lines, precise leveling, a lot of those guys would consider that. Couple other things that are important with leveling. Line of sight errors. A line of sight error will cause an error in the rod reading. Okay. Again, that can be canceled by keeping your back sight and foresight distances equal. If your crosshair is not horizontal, now that would be due to the instrument itself. That just means it probably needs to be adjusted. So hopefully that doesn't happen. Error in leveling it. If you don't get your bubble perfectly centered, it's not really that big of a deal, but if it's centered a lot out, then you're not really getting a good number. Parallax, I talked about that the other day, but that's the process. You have to focus not only your distance, but you have to focus the crosshair itself. Without that, you have parallax, and you will have parallax in total station will also give you parallax. So probably the biggest sources of error that you guys are going to have is right here, faulty rod readings. I would say that just about everything we do, you're either going to be either too high or too low, all right? And that's going to be the biggest issue for most of you. Recording the notes, that gets pretty tricky for first-time people. So first couple times we do your notes, you're going to have a tough time with it. I guarantee it. But once we do this a couple times, you'll get the hang of it. So those are the big sources of error. Probably going to be faulty rod readings and recording notes. Not so much leveling it out because the bubble is easy to center. All right. So I think what we'll do is this is a good place to stop for today. I just want everybody to be prepared for Thursday's test. I want to have a good results on that, and then we will proceed. And I'll pick up with this stuff next Tuesday, and then we're going to run out and do our traverse on Thursday. So we'll be back in business then. All right. So let me just go ahead. I'm going to get out of here for now. Let me just discard that and see if there's any questions on anything before I turn you guys loose for the day. Anybody?
I'm good for now.
Okay. If you do have questions, make sure you contact me.